Hello, today we will continue with our journey in the exciting world of singular value decomposition, or SVD. We are going to see how this powerful mathematical tool can be applied in image compression using classic image of Lena. Let's get started. For starters, I will load some Python libraries, and then I'm going to open a JPEG file called lena.jpg, which is stored on my hard disk, and this code is going to plot the image, and this code is going to go to my location of the JPEG. It is going to fetch the file size, and I'm going to print the file size here. Also, I'm going to see the shape of this matrix. So let's just run this code. So as you can see, firstly, this is the image, and the size of the image is almost 2.29 MB here. And the shape of the image or the matrix is actually, it's a tensor. It is a three-dimensional matrix. So it is 1687 pixel by 3000 pixel by 3. And this 3 depicts RGB color for each pixel. So as you can see, we have 1687 pixel on the y-axis. We have 3000 pixels on the x-axis. And the color information is encoded in RGB. Since I don't want to use tensors here, I want to deal with matrices. So I'm going to convert this picture into grayscale and get rid of the color component. So firstly, I'm going to now convert this image into a NumPy array, and then I'm going to convert this into a grayscale image by averaging all the RGB values to one single value. This is what this piece of code is doing. It is taking the average of all the RGB values, and it is assigning one single intensity value rather than the color value, which will convert this image into grayscale. And then I'm going to print the shape of this grayscale image. And then through this code, I'm going to display the grayscale image. And also, I will double check the file size through this code. So let me just run this. And as you can see here, the shape of the grayscale image has not changed. It is still 1687 by 3000. What has changed is that RGB values have disappeared. So this is now in a matrix form rather than a tensor form. You can see it from here. And the size of the image, since I've saved it as a PNG file, so PNG file is a lossless compression. So the size of the grayscale image has increased slightly, and it is around 3.29 MB now. So we'll play around with this image and use our singular value decomposition to do image compression on this particular PNG. So how we are going to do this is using this piece of code, where I'm going to be calling a linear algebra, a function from linear algebra library of NumPy, which is singular value decomposition. And I'm going to pass on this array, Lena Gray. If you can see here, this is an array here. So I'm going to pass on this to this function, singular value decomposition. And what it will generate is our three matrices, U, S, and V. And as we all know, U contains the right singular vectors, V contains the left singular vectors, and the S matrix contains the singular values. And U and V are orthogonal to each other. So let's just run this code. I need to comment this line out. Yeah. So let me just run this code. And you can see here that my U matrix is 1687 by 1687. My S matrix is not a matrix, actually it's an array of 1687 singular values. And the shape of my V matrix is 3000 by 3000. Now this is tallying with the image itself. We know that the y-axis is 1687 pixel, the x-axis is 3000 pixel. So now what I plan to do is that I want to once again multiply these three matrices together to get back to my original matrix, which was this Lena Gray, and prove it to you that this decomposition has actually worked. Now to do that, just pay attention to the dimensions of these matrices. So this is the U matrix is 1687 by 1687. Unfortunately, this S matrix is just an array, it's a one-dimensional array. This is how Python code works, this Python function works. So we need to convert this. We know if U has to get multiplied by S, then their dimension must be compatible. So that S must have a dimension of 1687 by 3000, so that U gets multiplied by S and S gets multiplied by V. So to do that, I'm going to initialize empty matrix, a zeros matrix of dimension 1687 by 3000, and then I'm going to pass on these singular values. This itself are singular values. So I'm going to pass on these singular values as a diagonal to this particular matrix, and this particular code is doing exactly the same thing. It is passing on the singular values as a diagonal of S, and then this S is of the dimension 1687 by 3000. And now I'm going to multiply all these three matrices together. U multiplied by S multiplied by V. And then this all is the plotting code. So let me just run this code. It'll take a while. So here we are now. We have three matrices, U, sigma, and V. U contains the left singular vectors, V contains the right singular vectors, and the sigma matrix is actually containing all these singular values. And as you can probably see you can see a diagonal that is passing through. These are 1687 singular values that are residing on the diagonal of this particular matrix. Please note that this is not a square matrix. This is 1687 by 3000, so it's not a perfect diagonal. The rest of the values are all 0. So when I multiply these three matrices together, I'm able to reconstruct my original image. This was my original image, and I've been able to reconstruct it by multiplying these three matrices together, which means the singular value decomposition is working fine. Note this is a heat map, not an image file, so the image is slightly blurry here, but we'll correct this. So what I want to do next is I'm going to plot these singular values, basically these diagonal elements, because these are very important. They are the ones which are capturing the patterns inside the data. So I'm going to just have a look at these singular values here, and I'm going to plot them. Essentially speaking, I'm going to plot this array S, and then see how do they look. So here we are. So I have my x-axis as singular values. So remember, we have 1687, and we then also have the magnitude of these singular values. And the highest magnitude is the first principal component, or the first singular value, and then it starts to fall drastically. And after a while, I think after almost about 50 principal components, these rest of the components become almost 0. And on the right hand side, here is the zoomed version of the left plot. So here I'm plotting all 1687 singular values, and but in the right plot, I'm just taking the first 30 singular values. And you can see that the first one is having the largest magnitude, the second one, third one, almost about all of them have non-zero values, and they are important. And beyond that, they all are becoming very close to 0, and we can ignore them. And this is exactly what is used for compression. All the unimportant features in the data set, we don't consider them, and that leads to the reduction in image size. So once again, I'm going to reconstruct my S matrix. Essentially, I'm going to again do this part. I'm creating a 0 matrix, and then I'm passing on my singular values as diagonal elements. This is what this particular piece of code is doing. Now here, instead of passing all 1687 singular components on the diagonal, what I'm doing is that I am actually using, through this variable, number of principal components, I am basically deciding how many of such components should become part of this particular S matrix. And this is having a value because this will lead to image compression. This will allow me to handle the image compression. So again, through this for loop, basically I'm creating, this was a 0 matrix having shape 1687 by 3000. And then I'm passing on, say, 11 singular values as a diagonal of this particular as a diagonal of this particular matrix through this code. Essentially, SII is representing the diagonal, and this is equal to the SI value, that is the singular values in the array. So let me just reconstruct this matrix with just 11 components now. So essentially what I've done is instead of taking all these 1687 principal components, I'm now just taking first 11, which is till this point, and using this I'm trying to reconstruct this original matrix. Obviously some piece of information will go missing because I'm just using 11 principal components. So, and again, so with this I am reconstructing my image, and again matrix multiplication takes place here, and I construct this as an array, and then I'm going to save this as a reconstructed image as a PNG file, and then I'm going to calculate its size, and also I'm going to calculate its percent compression ratio. That means with the grayscale original image, how much we have been able to reduce the size of the reconstructed image. So, and then we're going to display these images side by side, and rest of the code is for the plotting purposes. Let me just run this one. So the size of my reconstructed image has dropped to almost 1.1 MB. Remember, my original grayscale's image size was 3.29 MB, and this has resulted in a compression of almost 295%. But actually, if you have a look at the pictures, the left one is the original grayscale picture, and this is the reconstructed picture using just 11 components. But as you can see that this is pixelated, so let's just play around with this principal components, and instead of let's start with just the first one, the most important one, this one. Let's just start with this one and see what it does. So instead of 11 principal components, let me just start with one, and as you can see that it creates the low spatial frequency signals in the data set. So basically white, black, and this portion is again white, and this portion is again black, and then white. So this is the most predominant principal component, and it has almost, if I just used only the first component, it achieves a data compression of almost 534%. You can see that this reconstructed image is having size of only 617 kilobyte, whereas the original image had a size of 3.3 MB almost. So let's say that not one, let's use say first 5 components. So you can see that image quality has improved slightly, though it's still pixelated. The compression ratio has dropped, the image size has increased, but we are on the right track. Let's say we take the first 20 components, that is the first 20 principal components. That means all these from here till this point, and let's see what impact it has on the image. So you can see that the image quality is improving, though it's still pixelated. And as you can see, the size of the picture has slightly increased now. It is almost 1.2 MB, and the compression ratio that has been achieved is 260%. So let's say I take first 50 components. So now you can see that I have been able to recover almost everything from my original picture. Pixelation has gone, and I have been able to compress my image to just about 1.6 MB. The original was 3.3 MB almost, and this has resulted in a compression of 199%. And at the same time, there's very minor difference in the picture quality. And this is how we use SVD to do data compression in audio files and video files and image files and in data. Basically, we just extract the principal components or the singular values, and we use the most prominent ones, the most dominant ones, to construct our data set, to reconstruct our data set. And now, in fact, we can do something more. We can leave out the first, say, few principal components. Let's say instead of starting from most dominant ones, let's say we start with the 20th principal component, and we go to 200, and you see what happens here. So you see, it is now capturing high frequency spatial frequencies in the image, and in spite of the fact that the first 20 dominant principal components, that means from here to here, are not used. So you can see it is acting some a kind of filter. We can in fact instead of using we can say that let's use from principal component 50 to principal component 200, and you can see the image. Or we can also say that let's use first 100 component, not first, from 100 component onwards, let's use till 1000. And you can have a look at the picture. It is basically capturing different spatial frequencies in the data, and that's also impacting the image compression size. Now this image has become 2.3 MB, and the compression achieved is 141. Obviously, the higher principal components are not capturing the most essential part of the picture. They are capturing the high frequency components of high frequency spatial frequencies. So we need to incorporate the most important principal components. So let's just go back to 50, and let's have a look at the image. So yeah, we are back with the almost perfect image, perfect replica of the original image, and yet we've been able to achieve a compression of 200%. And the image size has reduced to 1.6 MB from 3.3 MB. So that's all in this video. I'll see you in the next one.